compare the results with the analytical, compare their numerical results, what they have got with the analytical results that you got using the equations, and the error is very, very huge. The reason is that because last time Dylan asked me about the geometry, and before Dylan asked me, and I told you the geometry of the specimen, right? So I give you two versions, but that version is not what it is supposed to be. Okay. However, if you are consistent, I'm okay. You don't need to compare, but I still need to see how you extrapolate the data points and to get the intercept. You understand? Okay. If you are using the geometry that and closely related using geometry that I give you, supposedly the result you get should be comparable with the results you get using the equation. But if you are using other geometry of the specimen, your results will be different, very different. As I said, as long as you are consistent, as long as you give me the sigma yy distribution and also sigma iyy multiplied by square root 2 pi x, and that distribution, then you just get rid of some points near the crack tip, and then you do the extrapolate using the straight line, and this straight line intersects this y-axis at a point. As long as you can show me this, I'm totally fine. Okay, so this is about the quiz. Then we talk about when this plasticity area is very, very huge, and we cannot use single parameter model to describe the stress, the crack tip field, and then we need to use two other models, and we have talk about one is called the KT model, and K is the Ki, right? This is the Ki. So T is the stress, and T is a stress value. So this is two KT model, two parameter model, and then we talk about the JQ model. So this is the second two parameter model. And we also talk about, so this is the different criteria, crack tip, different criteria will have different results. And you can see the string controlled, we have talked about the string controlled fracture, and also talk about the stress controlled fracture. And stress control, and the GC is a critical value, and it can be very sensitive to the Q, for the JQ model, and such as cleavage in metals. So this is the stress control, and then we have strict control. The fracture is less sensitive to the crack tip constraint. Here is one model. Okay, some genius they give us a model that combine the stress control and the strain control. So this model says that, and suppose fracture occurs when a damage parameter phi reaches a critical value RC ahead of the crack tip. The phi is given as this one. So this is the phi. This is the phi value. The sigma m and divided by sigma 0. And sigma m is the mean stress. And I want you guys to write down, okay? So sigma m so this is sigma m, and sigma m is the mean stress. And mean stress is also called hydrostatic stress. So what is the hydrostatic stress? So this is sigma m equals, and sigma m equals 1/3 and this is a sigma 1 plus sigma 2 plus sigma 3. So these three guys are three normal stresses. So this is called mean stress. And sigma, this is sigma 0, and sigma 0 is the reference stress. And then we have epsilon PL, and epsilon PL bar, epsilon PL and bar. So this is the equivalent plastic strain. Equivalent the plastic strain. Okay, so this equation says that, and this phi, the diameter parameter phi, is defined as sigma m, the mean stress, and sigma 0 yield stress, and this is material parameter, and sigma m is dependent upon the loading conditions. And so this is exponent gamma, and multiplied by epsilon PL. This is effective equivalent plastic. PL means plastic strain, and so it combines the stress control and the strain control. Right? It's stress this is sigma control is the stress control, and epsilon control is the strain control. And for this gamma is from 0 to 1. If gamma equals 1, so this is a full stress control. You can see if gamma equals 1, so this one exponent equals 1 minus 1, 0. So this one, the whole thing will be equal to 1.0. So that means plastic strain does not make any sense. Only this is the stress. And when gamma equals 0, and then so this is the full strain control. That means so this phi is a damage parameter is only related to the plastic strain. So this is how we define the full stress control and the full strain control. So however, if the gamma is located between 0 and 1, and we call combined, right? We call combined. So this phi will be compared with the phi c, and phi c is a critical the damage parameter. So you need to do experiments to characterize it. So you get this as phi c, which is a critical the parameter of the material, and then given a loading condition, and you can get a phi based on this equation. Then you compare, and so this phi with your phi c. If this equation is satisfied, that means it is very, very critical state. When the phi is a little bit greater than phi c, the failure occurs. So this is a failure. Any questions regarding this? Then, usually this is the sigma failure. Okay, sigma failure. We use the 0.3 multiplied by sigma 0. Sigma 0 is a reference stress, and which usually equals the yield strength. So sometimes when the n equals 10, n is the material hardening exponent. When n equals 10, and we use gamma equals 1, it means that is a stress control. And then we estimate the J critical over J0 and using the relationship of QT and to get a Q. So here we use this one. We use a beta. We talk about this ratio, the biaxial ratio, and T square root pi a divided by Ki, and let this guy equals this -1, and we know Ki equals sigma pi square Ki, and for this central crack. I'm sorry, for this is edge crack. And so then we can get T, let T equals minus sigma, and so this T equals 0.3 and sigma 0. Right? So usually we Q and it's around minus 0.28, and then we can calculate the J critical over J0, and which equals 1.8. So we have learned this two parameter approach to describe crack tip, and K2 theory, and K2 model, and JQ model. And there is another scaling model, and scaling model we will not talk about this one here, and we just talk about KT model and JQ model. And if you are interested in the scaling model, you can take a look at the notebook. Any questions? And my bottom line is that if I ask you guys if the elastic deformation is too big, and what kind of two-parameter models we have learned to describe the crack tip field? And the answer is KT model and JQ model. Can you write down, guys? So this is a two-parameter. If the plastic strain is, if the plastic deformation is small, and we can use the single parameter to describe the crack tip. The single parameter can be K and can be T, energy release rate, can also be J integral. However, if the plastic deformation is huge, single parameter models fail. And we need to use two-parameter approach, two-parameter model. One is called a KT model, one is called a JQ model. And definitely there is a scaling model. Scaling model, we will not talk about this one. I think for you guys, as long as you know KT model and JQ model, and I think you both will be very, very happy with your knowledge. Okay? Questions? No questions? If no questions, we talk about single parameter models, and then we talk about the two parameter models, KT and JQ, and then we have another question. So, when the deformation is too large, two parameter approaches break down. That means KT model and JQ model do not make sense. So, what should we do? So, limitation of two parameter approaches. You can see, okay, for low level deformation, so I just summarize here. For low level deformation, we can use single parameter K or G, and K is the stress intensity factor, and G is energy release rate. And so these two guys are interchangeable. And J is a J integral, and CTOA, CTOD, or CTOA. And we can, and so with single parameter, and we call this is a single degree of freedom. So however, if the deformation is intermediate, so then we use two parameter approaches or two parameter models. And as I said, we have KT and JQ and scaling. Even though the scaling I did not talk, you should know there are three, okay? So if we have extensive deformation, multiple, that means based on this theory, based on this logic, single, two parameter, and then if the deformation is extensive, and we are supposed to use multiple more than two parameter the model, and then some people ask how many parameters and will be enough. So here is some people have done this with us. And in the case of plane strain, we talk about plane strain here, the crack in a power law hardening material, and we use symptotic analysis and leads to the following power series. This is sigma ij, okay? And sigma ij equals k equals 1 to infinity, ak is a parameter, and j is j integral, alpha is dimensionless factor, epsilon 0 is the reference strain, epsilon sigma 0 is reference stress, and this y is one value, okay? So it is sk sigma ij wave and k and theta n. When the k equals 1, so this equation reduces to HRR equation. Okay, you can see here is my observation. When k equals 1, so this equation reduces to HRR equation. So the exponents sk and the angular function and for each term in the series can be determined from a asymptotic analysis. The amplitude for the first 5 terms are given as follows. For the first terms, for the first 5 terms, they are dominant. So as long as we can get this is 5 parameters, And for all the remaining terms, we can just ignore. Okay? And we still can have decent accuracy. So A1 through A5, so these 5 guys can be determined using this value. So this N is the material hardening parameter N. So this is In minus 1 over N plus 1. So A3 is A2 squared divided by A1. A5 equals A2 cubic divided by A1 cubic, A1 squared. So this is A2 and A4, and they are unspecified, and they are dependent upon external load and geometry, and they are governed by the far-field boundary conditions. So A2 and A4, and they are dependent upon the external load and geometry. So A1, you can get this A1 first, okay? So the first 5 terms of series have 3 degrees of freedom. And we have for this 1, 2, 3, 4. For these first 5, they have 3 degrees freedom. What they are? They are J, okay? J value, definitely. They have A2 and A4. Because In is dimensionless, and A2 and A4. And so these 3 guys, they are independent parameters. For all other A1, A3, A5, as long as we have these 3 guys, and we can determine them. Okay? So you can see J, A2, A4, and they are independent variable. Why J is very, very important because the J is here. You can see J. And so for this low and moderate, the street hardening material, the force independent parameter does not appear for many terms, e.g., for example, when N is the hardening material hardening exponent. When N equals 10, the force independent coefficient appears in this wave in the 100th term. This 100th term is very, very small, right? So thus, for all practical purposes, the crack tip stress field inside the plastic zone has 3 degrees of freedom, J, A2, A4. So this means that practically we need only 3 degrees of freedom to characterize the crack fracture. We need J, A2, and A4. Questions, guys? No questions? So we have learned single parameter models, and we have learned 2 parameter models. Now this one, if the deformation is too huge, and we can use the 3 parameter models. Okay, yeah, you can see 3 parameter models will be okay, will be good enough. Any questions, guys? Now, up to now, we have finished all these chapter 3. So chapter 1, chapter 2, chapter 3, and we talk about the series, the G, J, and K, and how they we derive them. And this is series. And from now on, we are going to focus on. We're going to switch gears to other topic. Right? So the most important things, most challenging things we have learned, and for the following things, and I think you will like. Any questions regarding K, G, and J, and CTOD and CTOA? If no questions, and we are going to switch gears to next topic. For this topic, I think this is close to you, and they are not extensively mathematically extensive. So, and I think you will love it. You will love it. So, questions? No question? And then we talk about this fracture mechanism in metals. So within this topic, fracture mechanisms are in metals, and we have the 4 mechanisms. And so one is called microvoid covalence. So the microvoid covalence means that, and we have, suppose we have pre-existing, this is microvoids, okay? And they are very close, but even though they are close, but the materials are connected together, and this is not break. However, if you keep loading it, so these microvoids will come together, and then, so this is combined voids, and it will look like a crack. This crack and propagates. So this is called microvoid covalence. So this is especially for the ductile material. The second one is cleavage. As the name suggests, and cleavage means that when the crack starts, and if you do not do anything special, and it will propagate until it fills, until this is the specimen becomes two parts. So this is usually for brittle material. So for this brittle material, so this is transgranular. And what is a transgranular? And as the name suggests, granular means grains, right? Right, guys? And transgranular means that the crack will cut through the grains. For example, here, look and see. This is my first. I just schematically I draw the grains. Okay, the 4 grains. The 4 grains. And these 4 grains, the crack, and just go through these 4 grains, not necessarily 4, and go through all these grains, and we have the crack. These crack propagates. So this is called the cleavage. And this third one is intergranular fracture. As the name suggests, inter. So intergranular means that so this crack does not go through the grains, and however, it just the crack propagates along the weakest points where is the grain boundary. Right? Usually, grain boundary is suppose you learn the material science, right? Right, Carlos? You learn material science? Yeah, sure. Are you learning now or are you finished?
What?
Material science.
Oh, yeah, we took it.
You're taking now.
No, I already took it.
Oh, you took it.
Yeah.
So these are 4 grades, okay? For this, suppose my 2 feet, they are 2 grades. So this is 2 grades. So for this cleavage means that the crack goes through these grades. Okay? However, on the contrary, for the intergranular, the crack do not go into the grains, and they just follow the grain boundary. Why? Usually the grain boundary and the bond is smaller, and you can just use very, very low energy to crack it along the grain boundary. So the fourth one is a fatigue and fracture. And fatigue fracture, if you have taken the machine design with me, fatigue means that we have, even though the load magnitude is small, but I just have cyclic loading and bend this way, back and forth, back and forth, back and forth. So the positive, negative, positive, negative, even though the load level is very, very low, but as the time goes, the specimen will fracture. So this is called fatigue. So this is the 4 failure mechanisms. Then look at this is for the first one, the ductile fracture. So this is a ductile fracture. So this curve, we are very, very familiar with this curve. Energy, annealing strain, annealing stress. And so we have this curve. So this is plastic, elastic, and then it yields, and so it hardens, and at this point, and it is this ultimate strength, heaviest one, and then at some point, the specimen is necking. You know necking, right, guys? Just like our neck, right, guys? Can you tell me what is the difference between our neck with our body? The neck is smaller, right, than the head, than the torso. Do you guys agree? Necking is very, very intuitive. You can see originally it is so big, but at some points, so at some locations, it is necking. Its necking means that at some location, the cross-sectional area becomes substantially smaller than other locations. Right? So this is necking. It's called necking, and then it goes down until it fractures. So this is for engineering material. Engineering material means usually they are not the pure material. They are alloys. Right? For example, the iron. And in our engineering applications, seldomly people are using the pure iron, right? Because pure iron does not make sense to us. What we use? We use this is a steel. And what's the difference between steel and iron, guys? Can I ask you a question about material science? Bobby?
Does steel have like coal in it? Is hardened by carbon atoms?
Yeah. Steel actually is alloy, right? We call alloy, generally call alloy. It is a combination of this is the iron and the carbon, right? Do you guys agree? Yeah. So you can see for pure material, especially for the pure iron or pure copper, if you do this kind of tensile testing, and it will be very, very beautiful. You can see, so just like is a straight line, and so at some point it breaks. And however, for engineering material, suppose we are using steels. Steels, as I said, steels is the alloy of the iron and the carbon. Maybe you have some and other alloying elements, for example, chromium for the stainless steel. And usually you will have this kind of fracture the surface. This is about 45 degrees. Right? And then after that, then you just stop. You just have a relatively flat breaking surface. Okay, so there are three stages. The first one, the void nucleation, and by either interface decohesion or particle cracking. So nucleation, you guys know the nucleation, right, guys? Nucleation. What is the nucleation? What is the nucleation? What is the nuclei?
Like the central particle.
Yeah, the central particle. Nucleation means that if you have learned the material science, and from the molten material to the solid material, right? At the very beginning, if you lower the temperature, what will happen first? And you will have nucleation. Nucleation means that some points and you will have the solid points. And then the solid points will grow bigger and bigger and bigger. And then this is the neighboring solid points when they grow bigger and bigger and they connect together, right? So finally, the whole molten material becomes a solid material. You guys still remember? Now here, the same thing. No, the very, very similar thing. Void nuclear means that at some point, and we have the voids first, right? Make sense? And based on what I just told you and how this molten material solidifies, and this is at some point they have solid material first, and then the solid material become bigger and bigger and bigger. Now here, the void, we have some points, some void start first, okay? Then these voids and they grow bigger and bigger and bigger. When the voids grow bigger and bigger and bigger, they connect together, the crack. It becomes bigger crack. So this is void nucleation. Then the void grows, just like the nuclei grows in the solidification. The void grows around the particle by means of plastic strain and hydrostatic stress. Void grows. Void, the void means growing. And then the void, neighboring void, coalesces with one another, and the growing void with adjacent voids, and then become a bigger crack. Right, guys? Are you guys okay with this one? So this is very, very similar to the process of molten material solidification. You can see void nucleation. So this is proposed by Argonne et al. And they argue that the interfacial stress at a cylindrical particle is approximately equal to the sum of the mean stress and the effective stress. And what is the mean stress? It is a hydrostatic stress. Okay, so this is mean stress. What is effective stress? The vomicis stress. And so who have learned the vomicis stress? Please raise your hand, please. Carlos, have you learned the vomicis stress? No? Okay. Vomicis stress is a combination of all these stress components. Right? So, and here is vomicis stress. So you can see the decohesion stress is defined as a critical combination of these two stress. So here is a sigma E is effective stress or vomicis stress, and sigma M is a mean stress, and equals C, sigma C is critical stress. If the sum reaches this critical stress, and there is void. Right? So what is the sigma M? This is sigma M. And sigma M equals 1/3 of these three normal stress. And you know normal stress, guys, right?
I hope so.
Hope so? Yes. Be confident. Okay. These are normal stress. So here is a sigma 1, sigma 2, sigma 3. What they are? What do we call if we have only one single the subscript for the stress sigma? Okay.
Normal stress or the principal stress or?
This is normal stress. If we have a single the subscript, they call the principal normal stress. Okay? Principal normal stress. What is the principal normal stress?
It's like Moore circle, that would be where there's absolutely no shear stress.
Yeah. Okay? Moore circle, it is on this is the x horizontal axis. And the more intuitively means that on this surface we only have normal stress. Shear stress equals 0. If you have not learned this one, I want you guys to write down as okay. The principal normal stress means that on this surface, shear stress equals 0. You only have normal stress. So this is the vomicis stress can be determined using this equation. That means, and we just use the three principal normal stress. So this is sigma M, and sigma M is hydrostatic stress. So no role in plasticity, but plays an important role to nucleation. So this one does not have any role in plasticity, but it plays an important role for nucleation, void nucleation. So according to Argonne et al. Model, the nucleation strain decreases as the hydrostatic stress increases. That is, void nucleation occurs more readily in a triaxial tensile stress field, and a result that is consistent with experimental observations. Right? So what is the triaxial tensile stress, guys? It's as the name suggests. So this guy has three surface faces, right? Three directions. For these three directions, all these three directions we have tensile loading. So this is a triaxial tensile stress field. So based on the Argonne et al. Criteria, right? So the barium, so this is original Argonne model, but this is a Bremian research group and proposed another one and based on Argonne's model. So you can see the difference between these two. You can see the difference, right? You can see the difference, guys? You see the difference or no?
Yes, yes.
You can see the sigma m is the same. However, sigma e, and he just the bringing, and he just include this is sigma ys here. Alright, so you can see that, and for this is the specimen, and even for longitudinal loading along with the transverse loading, and they are using the different coefficient values. For example, for longitudinal loading, and they use C equals 1.6, and for transverse loading, and they define C as 0.6. So they found this as a semi-empirical relationship and given better predictions of void nucleation at MS inclusions. So MS this is, and this is S is S is sulfur, right?
Yeah.
So Mn is manganese, sulfur manganese. So this one these inclusions. Assume ys is here means yield strength. So we just know this one, okay, guys? If there is a very the simple calculation, and you just know where to find this model. Trust me, guys. I will not give you the derivation here, okay? Okay, guys. The most challenging parts passed, and in the following weeks, we just enjoy the mass lecture. Okay. Or are you looking forward to the another answers morning? I'm kidding. If you want to let me know. So this is the second model. There is another model, the Goods, Professor Goods and Brown, and they develop a dislocation model for void nucleation and submicron particles. So they use this one. Okay, sigma 1, and sigma 1, as I said, whenever we see the sigma and that only has one single subscript, and they are principal stress, right? We usually, for 3D, we have sigma 1, sigma 2, and sigma 3. And sigma 1 is the largest one. Sigma 3 is the smallest one. I'm talking about algebraically. Okay? The sigma 1 is the largest one, and sigma 2 is intermediate one, and sigma 3 is smallest one. So you can see this equation. So alpha is constant, and there is a given range, 0.14 to 0.33. Mu is the shear modulus. The B is magnitude of Burger's vector. You guys know Burger? Do you know where you guys know the Burger's vector? Material science, in material science, we have learned on these dislocations, right? What's a dislocation, guys? Dislocation means that supposedly, for this perfect this crystal material, we should have some atoms in dislocation. But for some reason, some atoms in that area they are missing. So this missing is called dislocation. Okay? And how can we quantify the dislocation magnitude? And we use Burger's vector. If you want to know the details, you need to check the material science lecture notes. By the way, guys, how many semesters ago did you take material science? If you are not taking now. 2 semesters ago. What about other guys? Okay, so you need to check. Okay, Burger's. This is Burger's vector is used to quantify the magnitude of dislocation of this crystal material. The R is a particle radius. R is a particle radius. Okay, so usually the harder particles, and they are used as a nuclei. And then based on this harder particle, the void grows bigger and bigger and bigger, and with the center, this is the particle at the center. Sigma 1 is the first principal stress. If this equation holds, failure occurs. Is it okay? You know that, okay? If this equation holds, sigma, that means the critical point, and then the failure occurs. So this dislocation model indicates that the local stress concentration increases with decreasing particle size. So you can see R is a radius. The void nucleation is more difficult with larger particles. You guys agree? Yes, right? If you have a larger particle, it is more difficult to have a void around it. The continuum models we have learned will apply to particles with R is greater than 1 micrometer, implies that sigma c is independent of particle size. But this is observation. So experimental observations usually differ from both continuum and dislocation models. So this is dislocation model. So this one and this one, and they are continuum model. So in that, void nucleation tends to occur more readily at large particles, and further research is obviously needed to develop void nuclear models that are more in line with experiments. But this is observation. So here is other observations here. So it needs to be mentioned that these models and two continuum models, and one dislocation model, only consider nucleation by particle matrix bonding. Right? So we suppose we have particles in the matrix, and we only consider particle matrix debonding. And voids can also be nucleated when particle cracks. If the particle cracks, that is also nucleation. So large cracks are more likely to crack in the presence of plastic strain because they are more likely to contain small defects that can act like a brief crack. In addition, large non-metallic equations such as oxides and sulfides are often damaged during fabrication. Some of these particles may be cracked or debonded prior to the plastic deformation. So this is it's not theory based, it is related to the manufacturing processes. Okay? So we can see this is we have 4 mechanisms, and for the first one, Dardoux factor, we have 3 stages, and I'm told we have learned 3 models and 2 continuum models and 1, and this is the dislocation model. And then we talk about this void nucleation, and then this is Wednesday we are going to continue to talk about void growth and covalence, and there are several models here also. Okay, there's a lot of fun here. Okay. Any questions, comments, remarks? And if there's no comments, questions, remarks, I'm going to end today's session. And I hope you have a wonderful Monday, and also do your best to finish the quiz 1 before you leave for the fall break. Okay, that's all. Yes. Okay, if you have questions, come to my office and ask. All right? You're welcome all the time. I will see you. This is